All right, guys, here we are. We're starting on section 3 now. Okay, so I wrote myself a little reminder for how to assign anodes and cathodes. And in order to, what I want to do is remind myself by writing out some kind of a mnemonic, just like oil rig. So I write oxan and red cat. So what that means is oxidation happens at the anode and reduction happens at the cathode. So for this particular reaction, you get a lot of description of what's happening. And I will remind you that in our book, in our diagrams, we have something called a salt bridge, and I'll go. So we're talking about galvanic cells. You have a salt bridge, and then you have a wire connected to some kind of a voltmeter that connects the two. And that wire is connected to a solid on both sides. Okay. And then in each one, there is a solution of some kind. So that solution is usually a part of the reduction oxidation equation that's happening on either side. So we are going to, as is classic, put the anode on the left and the cathode on the right. And we have our galvanic cell. Now our goal is to figure out what's happening on each side given the information we were given. And we were told that there's some kind of solution in one beaker and then there's a solution in the other beaker. And something to remember is that potassium's not actually part of this reaction, so the K's are going to be ignored. And what we're going to see is that the potassium is attached to the dichromate ion, so the Cr2O7 2 minus, and the iodide ion, so the I minus on the left side. And then that we're going to be forming the chromium 3 plus somehow and the iodine 2, the I2 solid. All right, so what we're looking for now then is the oxidation reduction. And I'm going to guess that it involves chromium and iodine, mostly because I see chromium and iodine by themselves on the right side. So let's figure out which reaction. And since we balanced this earlier, one of the things to know is that the water goes with this reaction if it's balanced, as does the hydrogens. Those two things don't necessarily matter for this particular problem because all we're trying to do is identify anode and cathode by identifying reduction and oxidation. The signs of the electrodes are always going to be that anodes are negative and cathodes are positive. Remember, cat is cation, so you can also remember that being positive that way. Okay, so on the left side of our reaction, we want to figure out what chromium is, and then on the right side, we want to figure out how it changes. Obviously, we know that chromium becomes a 3 plus. What we need to know is on the left side. And if you recall, we've actually seen this problem before, but chromium turns out to be a 6 plus ion on the left. And since it goes from 6 plus to a less positive number, that means that it has gained or lost electrons. And I'm going to let you kind of think about it for a second. 6 plus going to 3 plus means it would actually have to gain 3 electrons. And then the other reaction, since we know that this one gained electrons, and gain means reduction. We know that the other reaction that we form, which is the one with the iodines, is going to have a change from -1 to 0 because elemental, remember. So when this guy does this, this is going to be a loss of electrons, which means oxidation. Okay, so what that means then, and we have our little mnemonic to help us remember, is that the reduction is going to happen at the cathode. So that means the chromium is going to be on the left side. The solution with the chromium 2O7 is going to be in the beaker. And the solid, or the metal, chromium 3 plus, is going to be the thing that's actually it's attached to. The cathode's going to have a similar situation. We were told that the iodine solution, so it's going to be I minus, and then the solid is going to be the I2 in this case. Okay. All right, so then that's the end of that one. It just wants you to describe the reaction occurring at the anode. So we did that. That's this guy. And it wants you to identify the reaction happening at the cathode. The direction of electron migration. So when we talk about voltaic cells, electrons travel from the anode towards the cathode. And then the direction of ion migration. So ions are actually going to go depending on their charge. They're going to go right or left. It just depends. Remember that in our example, ions tend to migrate positive towards the cathode, and negative ions will go towards the anode. Depends on whatever ions are in the salt bridge in this case. The signs of the electrodes are negative and positive as shown. All right, moving on. Section 4 wants us to calculate cell potentials under standard conditions. And the big thing to note, and there's a lot of little notes in here for you if you want to go ahead and take a look at these on your own, as to what is an electromotive force and how we define an electromotive force as a cell potential. If we want to calculate a standard reduction potential, then we need to take the reduction potential of the cathode and subtract the reduction potential of the anode. Now, all of these are written the same way, right? They're all written as reduction half reactions, okay? We do not write them as oxidation half reactions. And since they're written that way, what we're going to look for is each of our reactions down below, and they happen to be the same ones as up here. So we have this reaction and this reaction, and we're going to take both of those reactions and we're going to copy them back down here. So we know that our reduction reaction is the as written reduction reaction is going to be the Cr2O7 2-, making the 2Cr3+ and 7 H2Os. We're going to look for this reduction reaction the way it's written, and then since this is our oxidation reaction, we actually want to write it as if our oxidation is being reduced. So we actually want to write the reduction form of the reaction. So what that means is we're just going to flip it. So we're going to write 3I2 makes 6I-. Now, one of the things we're missing here is the electrons. If we want to, we can add them. So we can add our 6 electrons on the left to balance out these charges. And up here, then we would do, oh goodness, I don't remember, 12 versus 6. So we added, I think it was 6 electrons on this reaction. If the reduction reactions are written correctly, the electrons should be on the left side of your reaction. So the electrons should be on the side. Now, we may not find this particular reaction. We may find this whole reaction divided by 2, because that would simplify it. Oh, I'm sorry, no, not 2, 3. 6 divided by 3. So that would simplify this reduction equation to this. So we may be looking for that, and then we may be multiplying it, because when we have that amount, then we actually want to multiply by the number that we have. Okay, so next thing is going to be to find our half reactions. So up here we have a table. I see the chromate reaction. So here's the chromate. Let's find a highlighter. Ooh, the color's awful. Light color? That's better. So there's our one reaction, and it says that the reduction potential is a positive. Oops. So the reduction potential is a positive 1.33 volts for this reaction. For the oxidation reaction, which is the I2 to I minus, we find that one here, and it says that that one is a plus 0.54 volts. All right, so next thing to do is to do the E cell. And we know that this number is also, I'm sorry, going to be multiplied by 3 because we divided the whole thing by 3. So we're actually going to take that number times 3. And so we're going to get this value of, sorry, positive 1.62 volts. So then we're going to take the value and we're going to subtract them. So we're going to do cathode minus anode. And our cathode is the oxidation number, so that means this guy, the iodine, and that means this guy is our anode. So I'm going to remind you. So we're going to do, oops. So we're going to do E naught cell equals E naught reduction of the I reaction minus E naught reduction of the chromium. So I'm going to do positive 1.54 minus positive 1.33 volts equals E naught cell. And that value is going to be a positive number of positive 0.21 volts. Now, when that happens, what does that value actually mean is part of this section. So it has to do with if the value is positive, is it spontaneous or not spontaneous? And what we're going to assume is that if it's positive, that it is going to be a spontaneous process, okay? And that's part of our next section, in fact. And here's your next practice problem to do on your own. Cadmium and tin, set up a cell, so set up a voltaic cell where tin is the anode and cadmium is the cathode, and then show me what the standard half reactions are going to add to be for a standard cell potential, all right? The very last one that we're going to do is the EMF and Gibbs free energy. So a delta G equals negative NFE. And in order to do this, you first have to calculate E. And then once you have E, you calculate delta G by plugging in your values. And in order to do this, you're going to need to know the number of electrons transferred in each one. And so we're going to look at what these would have been before they were balanced. So yeah, all right, so let's look. So for A, we get this particular reaction would have had 2 electrons to balance out that number. And then we get the other reaction. And again, there would have been 2 electrons transferred in this process to balance out the 2 positive charges. So our N value then is going to be 2. F is a constant. So you're going to make sure you have that written down, 96485. And then our E is one that we are going to calculate. And with E, we're going to use the value that we calculate to figure out if it's spontaneous or non-spontaneous, as well as just calculate delta G. So E is going to be calculated by doing E naught, the reduction potential at the cathode, minus the reduction potential at the anode. From there, we gotta look these values up, I'm sorry. Okay, so we need one for copper 2+, and we need one for H+. So H+ is gonna be the standard hydrogen electrode. It's gonna be somewhere in the middle. There it is. Remember, everything is actually measured against that, so we know that the H+ is going to be 0. Oh, and look, that copper's right above it. So the copper has a 2+, has a 0.34 E value. Oops. And E naught reduction for this one is going to be 0 volts. And remember that in theory, you're actually supposed to flip the copper equation to find it on the table, but once you find it, you just write out what the reduction potential is, because copper technically is the oxidized one here. And so since copper is the oxidized one, copper is the cathode, and, no, I'm sorry. Since copper is the oxidized one, it is the anode, and the cathode is the reduction. So that's the actual H+. All right, so now we're going to calculate E naught. It says to take the reduction minus, I'm sorry, the cathode minus the anode, which is going to be that. And then we're going to get negative 0.34 volts. All right, so for this one, it says that E naught being less than 0 means it's a non-spontaneous process. So we can already label A non-spontaneous based on E. And then we can calculate delta G to be N is 2, F is 96485, and E is negative 0.34. And what we're going to notice is that delta G comes out to be a positive number. And remember that when delta G is positive, it is a non-spontaneous. So all this does is support our finding that the negative value is a non-spontaneous process. So this value comes out to be uh, 6560980 or that. Remember that this is typical. This rate here was just calculated in joules per mole, but we could divide it by 1,000, and we would get in kilojoules per mole, and that would be negative 6560.98 kilojoules per mole. Just pay attention to what it asks you. Oops, I'm sorry, positive. Delta G. Okay, so that was part A. I'm going to allow you to do part B if you want on your own, but really what I want you to do is this reaction. Okay, so part B is practice if you want to. I'm not going to go over because this video is already too long. And this is the one I would like you to do as part of your practice problem set. And just to reiterate, so this is the one you're doing for that last practice problem. This is the second one you're doing, this guy right here. And then the first one that you should have done was in the previous video, but it was this guy right here, balancing a reaction in basic conditions. All right, that's all. Have a great day.